In this video, I'm going to explain what we did in class, which was problem solving with diagrams. I would be using diagrams to solve problems, especially like word problems that involve acceleration. We went through these notes in class, so I'm going to use the handout to try and save time and just add a explanation to the handout. So when we diagram, there are certain characteristics that make it effective, and these are the same characteristics that I'm going to grade on problems where I'm asking you to diagram, as you'll see an example below. So the characteristics that make them effective that are required for the diagrams are to show the object at its initial and final instances. A lot of the variables we have, such as initial velocity and final velocity, are variables associated with each of those instances. So we want to draw those in the same diagram so that we can see, so we can attach those variables to the initial or final point. Things like delta x are going to be the difference between the initial and final position, right? So that would mean that we want to be able to connect the initial to final to show that spatial dimension. So it's important that we show visually the object in its initial and final states in the same diagram. In addition to that, we want to list what we know. Many times people will say, in physics, you list your givens. A lot of people will do this like just by making a table or a list of all the given information. By doing this in the context of a diagram, we're allowing you to see how it fits in, how it relates to the rest of the problem. We're not losing the context by just simply labeling variables like v0 equals 4, or a equals 2. It completely destroys the context of the problem when we just list the variables out. So we're going to list those variables out, but within a diagram, so it retains its context. So to do this, we're going to draw a labeled arrow for each of the given variables in the problem. We also want to do a labeled arrow for the variable that we wish to solve for. By labeled, I mean that it has a letter, the variable, set equal to a number in units. We want to make sure that we have the letter there so we can help to identify what equation we need to use based on what variables we have given. We also want to set equal to the number with units so that we know what values we're going to sub in for those variables and to make sure it's in the standard units. If we are solving for it, and obviously wouldn't know the number, then we can use it, we can set it equal to a question mark. I'll explain here using an example. So we have Estella here who's trying to figure out the acceleration she has while sledding down a hill. She measures the distance she slides to be 125 feet. She starts from rest, already on the hill, with no push, so she's already on like the slanted part of the hill, the incline. She's starting from rest, and her friend times it with their cell phone and gets 11.32 seconds for her to travel that 125 feet. Again, we want to know her acceleration. So we'll do part A first. I listed this in the same way that I'm going to list this on a test, where I'm showing you what I'm grading. So the diagram itself is worth 4 points. Sometimes it's worth 5 points. Equation is actually listed as 1 point. The substitutions into the equation and conversions are going to be worth 3 points, and the answer with units is worth 1. So all in all, this problem would be worth 12 points, right? Did I do that math right? Sorry, 9 points. 9 points. Okay, so the standard problem-solving approach that we're going to do here is to convert all givens into standard units. If it's already in standard units, great. If it's not, like this one in feet, I'm going to convert it to meters. So let's get all of our conversions done up front. We then diagram the problem, which I'll go through in a moment. With that diagram, we can choose the correct equation that fits this situation, and we then do the algebra that allows us to get the answer. So the first thing we need to do is recognize that the 125 feet needs to go into meters. So I would divide the 125 feet by 3.28, which is our conversion factor for feet to meters. Okay. As I diagram this, I'm going to show that I did that conversion, so I wrote 125 feet, and as soon as I write feet and I realize that, wait a minute, that's not standard units, then that would also remind me to do the conversion if I didn't already do it. Okay, so I'm showing then the object at the beginning and the end, and then I'm going to list all these variables with arrows. Time does not have an arrow, it's just how much. Everything else does have direction, so we can use an arrow for everything except for time. So you see v0, I'm going to put over the initial instance. A is constant over the whole thing, so I just put that kind of in the middle as a constant over the whole duration variable. That's what I'm solving for, so I set that equal to a question mark. Delta x is the distance it takes, or displacement I should say, from the beginning point to the ending point. It's how many meters we've changed. And we listed that as 38.1 meters, so delta x equals 38.1 meters. And like I said, time is going to be at the end, so I just put that somewhere towards the end. It says time is equal to 11.32. Note that I do not want to be an overachiever here and do something like this. Although there is a speed v at the end, it's completely irrelevant to this problem because I'm not given a value for it and I'm not asked to solve for it. So by including it, it actually will make it more confusing and put too much detail in my diagram. I want to keep it really simple. This allows me to do the next step, which is to take these four variables that are given and find what equation has that same combination of variables, those same four variables. For example, this one does not, because I don't have v. I would have a, t, and v naught, but I don't have v, so this would not fit the situation. If I had been asked to solve for the speed at the end, then this would be a good fit. But you can see since I don't have v in my diagram, then I shouldn't have v in an equation that I choose. I do want this one that's listed over here because it has delta x, v naught, a that I'm solving for, and time. So it's a perfect match and allows me to solve this problem. I then can do the substitutions, all with standard units, which means I get an answer with standard units. And if I'm asked to convert the answer for some reason, then I can convert the answer. So the conversions are pretty much done up front and at the end. It just makes life a lot easier. For part B, it says, assuming that x equals 0 meters at the bottom of the hill, which would mean that we're approaching the 0 meter mark on the tape measure as we go down the hill, we're going to sketch the graphs for this. It's a different situation here in terms of the direction, because now as this person goes down the hill, she's moving in the negative direction because we're subtracting position as we get closer and closer to 0. So delta x would be subtracting from 40 to 0. And everything else that's in the same direction, all the arrows in the same direction as that, would also be negative. So that means all of this is negative, whereas up here, it didn't matter which direction I chose as positive or negative, so I assumed that everything was positive. In a problem that you have, you can define what direction you like to be positive and then just be consistent with all of the arrows, unless it tells you what direction is positive, and then just use that. So since this gave me a tape measure, a position axis, along which she slides as she slides down the hill, that tells me it's negative down the hill, then all these become negative. And now I'm going to plot the shape of these lines. Right, position time, I know acceleration is going to be a parabola. That's from our acceleration experiment that we did. We noticed that this makes sense because if the velocity is the steepness or slope, as it gets steeper, it's getting faster. So we're going to start with a flat line representing a 0 velocity, and that's going to have to get steeper as she gets faster and faster, albeit in the negative direction. So it's going to end up with a negative steepness at the end, which traces out this parabola. For our velocity time graph, the velocities are now just simply y-axis values, so I'm going to plot 0 as my y-intercept, and then some negative value at my later time t. And that has to be a straight line because the acceleration is constant, and the acceleration is the slope. It shows how velocity changes over time. Since it's a constant acceleration of 0.6, then I would expect this to be a constant slope of 0.6. I hope this helps. Let me know if you guys have any questions.